In this lecture, we're going to talk about objects. We'll be talking about the basics of objects this week. In other words, we're going to look at what makes an object, how do we define objects in code, and what are some of the fundamental rules of objects that we're going to need to be aware of as we work with them this semester. We're not going to look at yet how objects interact with other objects or how objects scale to larger systems. This week, we're only concerned with the fundamentals of really what is an object, how do we define them in code, and how do we work with them. Up to this point, you've already done some work with objects, and you may have understood exactly what they were providing for you. Everyone up to this point has done some work with the scanner class, and maybe you've worked with the random class and a few other classes that have provided functionality via objects. This week, we want to look at how to go about building our own objects. So, what's an object? An object is a unique instance of a class with state, identity, and behavior. And we talked about this last class that objects have state. In other words, those are tracked through variables and properties, and we're going to look at how to set that up today. And objects also have behaviors, which are defined by methods, and we spent a lot of time last week just going over the fundamentals of methods, so we're comfortable with working with methods. And also, we'll look at this week about why I'm saying that objects have an identity, or in other words, why they're an instance of a class. So we're going to be defining our objects via classes, which is something you're already familiar with using in Java, but maybe not in the way that we're going to start using them now. So what's a class? A class is a blueprint or a template that defines an object's state and behavior. So think about this in terms of, say, building a house. Before anybody goes out and builds a house, what they tend to do is make a blueprint, set up a plan, figure out all the measurements, what goes where, how much the materials are going to cost, and so on. And from that one single set of blueprints, you can build many, many, many houses. So that's really nice. We can build one set of blueprints or one template for a house, and then from that, we can generate many, many, many instances of those blueprints. In other words, actual houses. You can't live underneath blueprints. I mean, you could for a little while, but if it rained, they'd probably get ruined. But you can live in a house. An house is an actual physical, tangible thing that can be worked with, whereas a blueprint is a concept of that thing. And we take the concept, we hire a bunch of people who build the house, and then we can live in the house. This is similar to our process of defining a class, which is going to tell us what our object is and what it can do. And then from that class, we're able to go ahead and generate objects. Okay, so let's start looking at this in code. I'm going to go ahead and define a really fundamental class that everybody can relate to. I'm going to call it pizza. It's really important at this point in the class that if you're someone who tends to not capitalize the first letter of your class names, that you start to do that. Now, one of the things that's really unique in this class, as opposed to other classes, is that we're not going to have a main method. We're going to start writing classes that define objects. In other words, that define the state and behavior for specific pieces of data that we want to use in our code. We're going to utilize those pieces of code in our programs, but the classes that we're defining are not meant to be run directly. So we have no main method, and we'll just make a mention of that here. No main method, as this class is not meant to be run directly. In other words, we're building a class that's going to provide functionality to other classes. So, now what we want to do is we want to start to think within this class of what the state of our pizza is going to be and what the behaviors of our pizza are going to be. So we could jump right into code, and some of you are very much code-oriented people, and that would be acceptable, but wouldn't it be really great if there was a language that we could use to visualize exactly, what our objects would look like before we built them? Because a lot of people are visual learners, and they look at code, and they look at this kind of blank slate in JGrasp and think, okay, I know I'm going to define an object, but I prefer to sketch things out on paper ahead of time, or I prefer to, visualize things a little bit more than code. Well, what's really great about that is there is this excellent tool called the Unified Modeling Language. And UML, as it's abbreviated to, because everything's abbreviated it seems in programming, is a great tool for us to go ahead and define our objects in a visual fashion. Throughout this class, what we're going to do is use UML to define our objects, You'll notice that there are some functions within the case tools, in other words, the UML software, that is going to allow us to generate our Java classes from the visualizations that we represent. So let's take a break from coding right now, go look at UML, and then we'll come back and we will finish up translating that UML into our pizza class that I have up on the screen. So we'll visualize it in UML, come back, and actually code it. So the tool I'm using in front of you right now is called Argo UML. It's an open source case tool. In other words, case tools are the names for the tools that are utilized to draw UML. Off the top of my head, I forget what a case tool is, but you can always go ahead and figure out what case tool stands for by Googling for it. So what are we going to do here? We've got this piece of software in front of us that provides us with the functionality to draw visualizations of data types. In other words, draw visualizations of the classes or the objects that are going to be generated from those classes. So there's a lot of stuff right now in this window. And I'm going to move my mouse up here to the top of the Argo UML window, and I am going to zoom in on that. And you'll notice that there is a button up here called New Class. So I'm going to click on it. And now it's highlighted. I can come back down into the palette window here and click, and I will get a class diagram in UML. Notice that there are three parts to this UML diagram. Up top, we're going to put in the name. So I'm going to say that this class is for a pizza. The top set of this rectangle, in other words, the middle piece here, I'm sorry, the top is for the name of the class. The middle piece is where we put our components of state. In other words, this is the variables that are basically going to represent our object's state. You'll notice on the left, I can put the name of a variable. So we'll put topping. And then on the right, the type of data that will be used to represent that. And so I'll put string for topping. Now I'm going to double click below it and I'm going to add another thing, another property here to my object. I'm going to add slices, so that'll be an integer because that'll track how many slices there are. Notice that this is integer. It's the object data type integer. If I want to, I can make it int. That's fine. And you know, maybe I'll do one other one called size. And we will do that as a double just because that'll be like, say, the diameter of the pizza, and from there we can calculate it. So what I have here is I have the name of my class, which is pizza. I have the three properties that I am interested in terms of my pizza object. Remember that objects in software are finite because we don't have an infinite amount of computing resources, we don't have an infinite amount of memory or time, so we just kind of pick those properties that we want to focus on when we're building our objects and are necessary for the program. But in the real world, obviously there's any unlimited number of components. And again, we're kind of building objects without a lot of guidance. One of the things that we'll discuss a little bit this week are what are called use case diagrams, which is this idea of figuring out why we're using objects specifically. In other words, how do users interact with the system and what kind of things are they doing? And once you figure out how a user interacts with the system, it becomes a lot easier to target exactly how you want to abstract out the state and the behaviors for. Now let's move down and start to add some behaviors to our object. Behaviors go in the third and bottom component of our object diagram. So first thing I'm going to do is name this eat slices, because I know one of the things I'm going to do if I have a pizza is I want to eat it. And we'll talk a little more about what that behavior does in a second. Now, there's a couple other things that you need to think about when you're dealing with objects and software. So unless you're Neo from the Matrix, you really don't have this ability to stick your head inside the computer and see all of the flowing electricity and the zeros and ones and actually look at the values that an object has in memory. So one of the things that we need to think about when we're building software objects is we need to write special behaviors that give our users the ability to look at the values or the properties of our object, because if they want to find out how many slices are left or what topping is on the pizza, they can't just see it. They need a way to ask the object what is on top of the pizza or how many slices are left. Sometimes you'll hear methods referred to as sending messages to an object. In other words, when we invoke a method on an object, we're really sending in a message, and that's a great way of thinking of this as well. So first thing we're going to do is set up a behavior for eating slices. The second thing we want to do is write some specific methods that allow users to look at or view the values that are being, tracking the properties of our object. So let's go ahead and do that. So I'm going to set up another method. Now, these types of methods are called accessors and mutators. In this case, we're writing what are called accessors. They allow us to view the properties of an object. In a second, we'll write mutators. They allow us to change the properties of an object. You can remember that word, but the reality is most people tend to call these getters and setters because these are methods that allow us to get properties and set properties on an object. So you'll notice that my method is called getTopping, and it's going to let me get the value that's contained in topping, and I'm going to have a method called getSlices because that's going to allow me to view the value in slices. And I'm going to have another one called getSize. Now, for example, if you don't want a user to have the ability to see any of those properties, you just don't write the get method for it, and then the user has no access to that property, which may be something you want to do. Now, notice when they get the size, what's the user actually getting back from this method? They're actually getting back a double value. And when they get slices, they're actually getting back an int. And when they get topping, they're actually getting back a string. So in UML, not only do we indicate the name of the variable or the name of the behavior, we also indicate data types that are associated with the data that we're dealing with. So let's start with getToppings. And we know that the topping variable is a string, so this method is going to return a string. So we can scroll down here to the bottom. And what I'm going to do is click on this method here, or sorry, down in the bottom area. You'll see that there's this whole area for properties and a lot of stuff that we can actually do to modify our objects. So notice that it automatically gives me this return value, and I'm just going to delete that because it always messes me up. Now, I can come down here and click on this little weird new parameter icon, and it's going to fire me into this window where I can give this argument a name, and I can also choose a data type for it. First thing I'm going to do is I know that this is returning a string, so I'm going to select string from the pull-down menu. Notice though by default it thinks that I want to input the string as a parameter to my method, but really what I want this method to do is return a string. So I need to come all the way over here, and you might be spawning screens on me, I don't know if you'll see this, and click the button that says return. And what that does is it indicates to the UML diagram that I want it to make a return value out of this. Notice that the format in UML for any method return type is to put the name of the method followed by a colon followed by the data type for the method that returns it. Notice that if you don't have anything after a colon, it's technically assumed that this is a constructor because the constructor is the only method that does not return a value. I mean, arguably you can also just go right in here and type it yourself. So slice is an int, I'm going to make that return an int, and size is a double. I'm going to go in and have that return a size. And notice eat slices. What is eat slices? Eat slices' job is to just go in and decrease the number of slices of my pizza every time I say eat slices. And so I'm going to have it return void. Because if I want to know how many slices are left, I can ask for slices. But notice eat slices is plural. It says eat slices with an S. So that means the user should be allowed to enter an argument that indicates how many slices of pizza they want to eat. So let's go back down to our properties. I'm going to delete this default property for the eat slices method. I'm now going to click a new parameter. I'm going to call it slices. Let's just call it, I don't know, num. How's that sound? And then I'm going to choose num to be of type integer because it's not giving me primitive values. We'll talk a little more about that. Make sure that the kind is an input parameter, and now you'll notice up here that eat slices is accepting an integer of type num, and I actually lost my, and returns void. Oops, and that's kind of weird. You'll notice that Argo is a little bit of a touchy program. Notice it keeps wanting to do that, so I'll go down and do it in the actual argument component itself. So I'm going to scroll down here, create a new argument. I'm going to select void, and then I'm going to come over here and make it a return value. And now Argo has set that up properly. So now here's what's really cool. We've taken the time to build our UML diagram. We've got this visual representation of our class that we can send to any other programmers so that they can, basically build our program. And you're saying, well, why would I take this extra time to do this level of planning? Here's what's really great about most UML tools. And we can go up to the menu, and you'll notice that there's a generation menu selection item. Go to generation. I'm going to say generate all classes. Notice I get a menu of different programming languages that Argo is aware of. And I'm going to click Java. I'm also going to go ahead and browse and select a program, select a directory for where I want to save that information. And now I'm going to just click Generate. And what has happened is that I have had that file, the Java file, generated automatically for me. And now you can see that all of my object's properties are here, and all of the behaviors that I indicated are here. And now all I have to do is go in and actually make some corrections, because there are some subtleties to using Argo that we're kind of skipping over here. And there are, in my opinion, better case tools out there that have more features, that are a little bit more rich, but we're just going to kind of work with Argo to the best of our ability. So we're going to have to go in and make some changes. But what's really nice is you didn't have to write this stuff up from scratch. Okay, so one more thing that we need to discuss is that we've looked at special methods called getters that allow us to get values in our object, in other words, our object's properties. But the other thing we want to take a look at is how do we write values that set values? In other words, we can read these values, but what if I want to change them? These methods, if you haven't figured that out already, are called setters. And we're just going to write one or two of them. This one's called setTopping. It's going to return void. So I'm going to type that right in there. Now what I'm going to do is come down here, create a new parameter. I'm going to call it T for new topping. We'll put new topping just so it's not confused. And I'm going to make its data type string. And I'm good. And now what I can do is I can click on that, make sure it's set. And I do want to make sure that it's indicating that that returns void. So I'm going to make a new component. I'm going to make it of data type void. And I am going to make it a return value. And now what I've got is a way to see what the topping variable is, and I've got a way to set the topping variable to a new value. And if I wanted to, I could keep going and writing new setters. So let's do one more for get slices or set slices, which would be really weird, but it doesn't really matter. So I'm going to come down here, delete that return value. I'm going to add a property. Make it a void return value, because notice that setters always return void. I then can go back. I'm just making sure this actually works. I can add a new argument, which I'll call new slices. I'm going to set its value to be of int, and I'm good. So now you can see the difference between methods that allow you to set the value of a property and methods that allow you to get the value of a property. And again, the proper name for getters would be accessors, and the more proper name for setters would be mutators. Okay, so we've talked a little bit about UML. We've looked at how we can use UML to visualize our classes, and we just looked at how we can use UML to go about generating our Java code for us automatically. But that's no fun, and we're going to actually get rid of that auto-generated file right now. We're going to go ahead and we're going to rewrite everything we just did, but we're going to write it by hand and talk about the organization of our file, and we're going to also talk about how to write those behaviors by hand as well. Again, once you get comfortable with this, you're free to generate your code prototypes straight out of Argo, or you're free to hand code everything. Whatever is up to you. When you get into bigger systems, UML diagrams get to be really helpful. All right, so what I'm going to do is turn line numbering on so it's a little bit easy to see. So we're going to write our class called pizza. Again, this class is defining a data type. It's not meant to be run directly, so there's going to be no main method. So the first thing we're going to do is define our state components. And we're going to make all of them private to enforce the concept of encapsulation. And encapsulation is this idea that we don't want anybody to mess with our object state unless they do it in a way that we deem fit. So we're going to go for a private string called topping. We're going to go for a private int slices, and then we're going to go for a private private double diameter. Now, what does this whole idea of encapsulation mean? Well, think about it. Let's talk about the number of slices in our pizza. We want to make sure that when people set the values of our object's properties, that they do things that are sane. In other words, we should never have a pizza with negative slices. We should never have pizza with a diameter maybe over 12 inches, I don't know. And we should never have a pizza that has, toppings like charcoal. We want to sanity check our data. So encapsulation means we set all of these variables to private, and you should almost always, without exception, set your object's properties to private. Yes, there are exceptions. It is often quicker to access a property directly than go through a method. So in instances of, say, real-time programming, game programming, we may choose every now and then to expose one of these as private. Expose these as public instead of private. But for right now, we're going to always make our properties private. So how does that allow someone to access them? And what in detail does private mean again? Well, private means any variable or method declared as private can only be accessed within the class in which it's defined. So in other words, this topping variable can only be accessed by code that is written in the pizza class. So if I were to write another class called my pizza store, I would not be able to directly access topping. Private means anything inside pizza.java can access this topping variable, and anything outside of this file, pizza.java, cannot access it. Public means anybody in any .java file can access it. So now let's go ahead and let's write our behaviors. So first things first, we want to write some getters and setters. We want to write accessors and mutators. Accessors and mutators are the behaviors that let users see our object's variables. Or let's just say our object's properties. Not just see them, but it allows them to see and change our object's properties. Let's start with those first. Let's write some accessor methods. So our accessor methods are going to be public. So the first one we're going to write is public we're writing getters, so public string get topping. And you're going to start to see a format for these methods. It's called get topping. It is somewhat related to the value that you're getting. It is always going to return the type of data that you're accessing, and it's probably always going to be public because you're using this public method to access this private variable. And all it's going to do is return topping. Now, this seems a little bit weird, and some other languages have more elegant ways of handling getters and setters. C# has a really nice process for this, but just know that, yeah, you need to write these if you have private properties in your object, because it's the only way a user can see what the values of those are. So let's go ahead and write one of these for both slices and diameters as well. So I'm going to call this one get slices. Notice that it returns an int, and all I'm going to do is return slices, and that is the value type of that variable. And next up, I'm going to have a double, because I'm going to have get diameter, and it's just going to return diameter. So now I've got 3 getters. This allows the user using our class to access each of these variables. Next up, I'm going to go ahead and write some setters. Setters return void because all they do is allow us to change a variable or a property of our object. So I'm going to go ahead and say public void set topping. I'm going to need to accept a string, and I'm just going to call it t because it's easy to write that at the moment. And all that I'm going to do is I'm going to take topping, and I'm going to set it to the value passed in as t. Why can I call topping directly? Because you're thinking, well, topping is private, but topping exists in the same .java file as this method, so it has access. Again, this code is written in pizza.java, this code is written in pizza.java, therefore they can access each other. And I can go ahead and I can start to write setters for other things. Now, I'm not going to do anything really special for the set topping method, but let's do something when it comes to set slices. So for set slices, I'm going to accept an int. Let's call it s for slices. And here's what I'm going to do. I'm going to do a little bit of a sanity check. I'm going to say if s is greater than 0, then I'm going to have it set slices equal to s. So here's what the real power of setters is. It allows us to look at the value that the user wants to enter for our property and do a little bit of sanity checking. And in this case, I'm just doing something really simple. I'm just going to say, hey, look, make sure that the user's entering a positive number. And if they are, then go ahead and allow that value to be set. So what's really cool here is that setters allow us to control what values our objects' properties are set to, which is really nice. And this would be important in things like, say, banking systems. If someone made a $4 billion withdrawal or a $4 billion deposit, you might want to sanity check that because it's not necessarily probably an accurate withdrawal or deposit. All right, so one more. I know this is getting a little repetitive, but that's the point. So public void get we're writing setters set diameter, and I'm going to accept an integer. I'm going to accept a double. I'm going to call it d for diameter, and all I'm going to do is set diameter. I can't spell anymore. Diameter equal to d. All right, so now we've got all of the setters and getters for a program. So we have a way to both read the value of topping and change the value of topping. We have a way to read the value of slices and change the value of slices and make sure it stays positive. We also have the ability to read the value of diameter and set the value of diameter. So a lot of students think, wow, this is really not fun code to write. And I agree, Java doesn't give us really good shortcuts for dealing with this like some other programming languages do. But you always, always, always want to enforce this concept of encapsulation. Your object state should be sacred. You keep it walled up. You don't let anybody directly access it. The analogy that I almost always use is, imagine if you walked into a bank and there was just a big bag of money sitting on the floor. And they just were going by the honor system that you could take the cash that's appropriate to you and you wouldn't take more than you had in your bank account. That would be some pretty serious honor system going on there. And the same thing goes if you make your variables inside of your objects public, then you really are at the mercy of the end user, and they could always set some really, really, really crazy things. So if anybody's ever dealt with data entry jobs or cleaning up data entry issues, you'll understand what I'm talking about. Okay, let's write one more method now that actually does something. So I'm going to write a method called public. Which one do we have? We had one called eat slices, so it's a void, and I'm going to write the eat slices method, and it's going to accept an integer. And I'm going to call that s. And what I'm going to do is this. I'm going to say, look, if s is less than or equal to slices, in other words, if the user is not trying to eat more slices than are left, like if there's only 4 slices left and, they want to eat 5, then they're in trouble. So what we're going to do is check to see that we have enough slices to eat. And then all I'm going to do at that point is I'm going to subtract the number of slices the user wants to eat from the total number of slices left. So I'll just say slices equals slices minus s. So now every time I pass in a number of slices to eat, I can check to see that we have enough slices. So now I have this really cool method that allows me to, if I want to eat 2 slices or 3 slices or 4 slices. Now let's try to modify our object one more time. Notice here that we've got, again, getter and setter methods. We've also got now one behavior that allows us to eat a slice. Now what I want to do is, you read last week about method overloading. So notice, for example, I have a method here called eatSlices. I'm going to declare another method called eatSlices. This method accepts a single integer method. This method is going to accept no parameters. So this method is overloaded. Why? Because it has the same name, but a different number, type, or order of parameters. So how do you think the eatSlices method should operate? Well, the reality is most people just eat one slice. So I'm just going to basically say if slices is greater than 0, in other words, if I've got slices left, slices minus minus. which will let me eat one slice. So now I've got some behavior starting to shape up here. And I'm even giving the user of my class some flexibility. If you want to just eat one slice, call the eatSlices method with no parameters. If you want to actually eat more than one slice, call the eatSlice method and pass in the number of slices that you'd like to eat. This is how a class should be organized. Notice that we've got the parameters listed at the top, commented, tightly put together, very obvious what they're doing. Then also note as you scroll down, we have our getters grouped together, our setters grouped together. You don't have to group your getters and setters together. Some people like to put get topping and set topping right next to each other. I don't care, however you decide to organize it. And then they tend to have the behaviors that are not getters and setters grouped together as well. So this is a good organizational tool for your class. Now, let's talk about constructors. Notice in our pizza class, we have no way to build a constructor, no way to build a pizza. Well, really we do, because if we don't declare a constructor, what we end up with is what is called the default constructor. And the default constructor is just given to you by Java. All it does is allow you to ask the Java runtime for some memory on the heap so that you can store a pizza object, but it does not set the default values of your object. So I'm going to go ahead and I'm going to set up a constructor. And constructors are a little unique, need to be public, should not have a return type. They don't return void, they don't return data, they return an object, and that's assumed. And they have the same name as the class. If I write my constructor like this, that accepts no parameters and does nothing, this is what the default constructor is. And remember, the book indicates, and I'm going to remind you right here, that if you do not put a constructor in your class, what you end up with is the default constructor. So you get something that looks like this. It just returns an object. As soon as you declare a constructor, no default constructor is assigned to you. So our constructor is going to set the default state of our object. So we're going to go ahead and we're just going to do string t, int s, and double d. So here's what we've got. We need to set the value of our topping slices in diameter, and so we're going to accept 3 parameters in our constructor, and we're simply going to go ahead and we're going to set them. Now, I already wrote a bunch of methods down here that allow me to set my values, so I'm just going to reuse them. I'm just going to call set topping t, set slices s, and set diameter d. And what's really cool about that is if I want to change any of the ways that I check my data to see if it's valid, I only need to change it in the set method. I don't need to change it in both the set method and the constructor. By the way, what if you want a constructor that just returns an empty object? Well, remember, once you define a constructor, you do not get the default constructor. So if you really want that functionality to be provided to your user, you need to declare it. And you don't need to have a default constructor all the time. It's up to you. But if you want a do nothing constructor, you have to write it if you declare any other constructors. And you can read that section of the book just to clarify that and ask on the discussion board.